Greg Cheney is not here. Video streaming too. So it's all yours. Go ahead.
May I start? May I start? Hello, can you hear me?
Yes, at least we can online.
So, may I start now?
Yes, you can start.
Okay, thank you. Thank you for your introduction. It's my pleasure to present my talk in this workshop. And I'm grateful to the organizer for the invitation. I'm sorry that I cannot join in person. Excuse me, what is this? In study of turbulence, much attention has been paid to asymptotic states or basic state in certain idealized conditions. For example, in K41, it is assumed that the Lens number is large enough and the scale is small enough, and the statistics are homogeneous and isotropic, and so on. However, in any real turbulence, viscosity, diffusivity, scale range are only finite, and the statistics are not homogeneous nor isotropic. Here, I call the difference of the real conditions from the idealized conditions as disturbance. Among many kinds of disturbances, I will talk here about the finite viscosity and diffusivity and mean field gradients. Needless to say, many studies have been made on the effect of these disturbances. It's impossible for me to review all of them. My discussions will be limited mostly to those from a viewpoint that is in a sense similar to the idea of linear response theory of systems at or near thermal equilibrium. My talk here is partly based on my knowledge by my works made under collaboration. My talk will be based on linear response theory, and my work will be based on my knowledge by my works made under collaboration with my colleagues Yoshimatsu, Goto, Ishihara, Mizuno, Morishita, Oi, Sogabe, Tsuji, sorry, I have to read, Uno, Yoshi Yamamoto, Yu Yamamoto, Yokokawa, Yoshida, Yoshino. That's all, and others. Now, in this talk, after a few comments on the background of my talk, I will talk about effects of finite Lens number and or Peclet number, and then talk about effect of mean field. Let me start with background. One may wonder why, one may wonder if disturbance may matter. One may then say it may matter because of the simple fact that disturbance such as 1 over Lens number or 1 over Peclet number is not zero in any real flow. One may also say that it may matter because disturbance may be not negligible. Consider, for example, the energy spectrum in the inertial subrange. According to K41, it is given by the well-known -5/3 law, or equivalently by the 2/3 law for the second-order structure function. Various intermittency models have been so far proposed. According to them, the so-called compensated spectrum or compensated structure function has a correction due to the intermittency, the scaling mu or mu prime. Here, the coefficients Ci and Ci dash are supposed to be viscosity independent. This figure shows the compensated energy spectrum by DNS with R lambda up to about 2000. The upper figure shows the spectrum as a function of K eta. Here, eta is a Coulomb length scale. The lower figure shows the same data, but as a function of KL multiplied with some power of R lambda. Here, L is the integral length scale. It is seen that there is a nice scaling range, say tilted range, T range. And the curves overlap well when it is plotted against xkl multiplied with some power of r lambda. This implies that the prefactor in this formula, Ci, is in the T range is not independent from viscosity. The similar is also true for the structure function. And it is also seen that there is another scaling range, say flat range, to the left of T range, and the width of the F range increase with length number. This looks to be consistent with Tsuji's analysis of atmospheric data. Here. One might think that if there is a certain scaling range, then it may imply that the range is a scaling range where the interpretation models are supposed to be applicable. However, these figures show that it may be not true. And this also suggests that the length number about r lambda 2000 or so may be not high enough for the test of intermittency models. Intermittency correction in the limit of high enough length number should be distinguished from the scaling at finite length number. Since my talk is based on an idea similar to that of linear response theory, LRT, of statistical mechanics for systems at or near thermal equilibrium, let me explain briefly about the basic idea of LRT. Suppose that an external force X is applied to a thermal equilibrium system with equilibrium density distribution rho E. Then, in response to X, the density distribution changes by amount of delta rho. And accordingly, the statistical average of observable, say B, change by the amount of delta B from the equilibrium value. And this delta may be approximated to be linear in the force X. Here, C is independent from X and determined by the equilibrium state. If the force consists of more than one kind, then this change is to be understood as the sum of the responses. Suppose that a system is at an equilibrium state, and if disturbance are added to the system in the form such as electric potential gradient or temperature gradient or density gradient or strain, then the system would respond in the forms such as electric current, thermal flux, density flux, and stress. And this response may be written symbolically as J equals Cx. Here, J is so-called generalized flux, and X is called generalized force. Presumably, the best-known example characterizing such response is Einstein's relation. It implies that the coefficient C, D in this case, diffusion constant, reflects the nature of the equilibrium system. And Onsaga's reciprocal relations also tells us that the coefficient C reflects the nature, in particular the symmetry property of the equilibrium state. Theories explaining these responses have been developed by Nakano, Kubo, Green, and others. Now let's consider effect of finite length number and or Peclet number in this order. My talk in this part is related to these four figures. Figure one shows the third order velocity structure function as a function of normalized distance, and figure two show mixed scalar velocity structure function as a function of normalized distance. And figure 3 show the Reynolds stress as a function of normalized distance from the wall. And figure 4 shows the Lagrangian velocity structure function as a function of normalized time interval. I was attracted by the similarity of these figures of so different phenomena. Let us consider first the Reynolds number effect of the on the third order longitudinal structure function, which is defined in terms of velocity difference of velocity at 2 points separated by distance r. This function satisfies the Kalman-Haworth relation. Here, DLL is a second order structure function, and epsilon is a energy dissipation rate per unit mass, and F represents the influence by external forcing. This relation may be written symbolically in this form. And if length is high enough, there must be a range of R that is much larger than Kolmogorov scale. Then this term may be negligible. And if R is much smaller than character length scale of forcing, then this is also negligible. And if the statistics are nearly stationary, then this non-stationary effect may be negligible. And consequently, we have well-known Kolmogov's 4/5 law. Many studies on the estimate of the R dependence of these terms have been made. They include, but not limited to, studies listed here. It's impossible to exhaust all the literature. From the viewpoint of linear response theory, they may be estimated as follows. Some more detail of the estimate may be found, for example, in my paper published in Journal of Statistical Mechanics. Let's consider first Reynolds number effect in freely decaying homogeneous isotopic turbulence. If the turbulence is freely decaying without external force, then the correction due to the external forcing is zero. And regarding the viscous term, the LRT suggests that delta nu is linear in nu. If we assume that equilibrium state is characterized a la K41, that is characterized by epsilon and r, then we may assume that this coefficient C nu is determined by epsilon and r, and then we have some estimate for this term. Here C nu is a non-dimensional constant coefficient. As regards the non-statutory term, the LRT suggests that the term is linear in 1 over t. Here, t is characteristic scale of time scale of energy counting eddies. And if the equilibrium state is characterized by K41 idea, then we have some estimate, that is CT is determined by epsilon r, and dimensional analysis gives this estimate. Consequently, the difference between the normalized structure function and 4/5 law is shown to be consist of two terms. This implies that the difference delta as a function of R take its minimum at certain value of R, that is R minimum. This minimum, delta minimum, decreases with R lambda in proportion to R lambda to the power of -2/3. These estimates are in accordance with the studies so far made, including but not limited to studies listed here. If the turbulence is at a statistically stationary state under the action of external forcing, then the non-stationary term is zero. And if the forcing is confined only to small wave number range characterized by L, then it is shown that analytically the correction due to the forcing is R over L square of order R. And the viscosity if the equilibrium state is characterized by epsilon and r, then we can estimate the viscous term in the same way for the decaying turbulence. And consequently, we have this expression. And this implies that the minimum of this difference as a function of r decreases with r lambda to the power r lambda to the power of minus 6/5. And this estimate is again in accordance with previous studies. This figure shows the data collected in Antoni and Buratini plus some other DNS data. And it is seen that the longitudinal structure function approach to the asymptotic values 4/5 in this case, minus normalized, and both in forced and decaying cases. However, the rate of the approach is different for two cases, and the approach is seen to be faster in forced case. Next, consider the so-called mixed structure function that is defined in terms of velocity and scalar difference between 2 points separated by r. For passively convected scalar field, we can derive an equation similar to Kalman-Haworth equation. Here, d psi is a second order correlation, and chi is a scalar dissipation rate, and f psi represents the effect by scalar input. This relation may be written symbolically in this form. And if Lane number is much large, then there must be a range of R that satisfies that R is much larger than diffusion or dissipation length scale of the scalar. Then this term may be negligible. And if the forcing the R is much less than the characteristic scale of force input term, this is negligible. And if it's the statistics are stationary, this is negligible. So that we have so-called Young-Rom's relation. And of course, there have been many studies on this relation. They include studies listed here, but not limited. Now consider Lane number or Peckel effect in the so-called inertial convective range of freely decaying homogeneous isotropic turbulence. If the field is decaying without scalar input, then delta F must be 0. And the effect of diffusivity and effect of nonsense term can be estimated in the same way for the case of Kalman-Haworth equation. Let me skip the detail here. The logic is very similar. That is, the point is that we assume that the equilibrium state can be characterized by chi, epsilon, and r in certain range called inertial convection range. And then we have this expression, and this implies that the minimum of delta decreases with r lambda in proportion to r lambda to the power of minus 2/3. These estimates are essentially in accordance with the estimate by Zhou, Kang, Menebo, and Tisset et al. The idea can be applicable also to the estimate of Lane number effect in stationary homogeneous turbulence in the inertial convection range. If the statistics are stationary, then the non-stationary term must be 0. And in the same way for the velocity field, we can show that the input term is in proportion to R over L square. And the diffusion term is also estimated in the same way. And in conclusion, we have this expression for the difference from the asymptotic value. And this difference, the minimum of this difference decrease with R lambda in proportion to R lambda to the power of minus 6.5. By the way, this estimate for the diffusion term is confirmed to be consistent with Kragland model. In Kragland model, the convection velocity is assumed to be delta correlated in time. And what is nice in this model is that we can derive exact closure equations for the moment. And one can implicitly derive the so-called anomalous exponent by analyzing so-called zero mode. And the scaling depends on this exponent C. And this figure shows the scaling exponent and the so-called anomalous scaling obtained for the case of two dimension by the analysis of zero mode and simulation and theoretical analysis as a function of Z. Recently, the idea of LRT was applied to the estimate of length number effect on the momentum transfer in turbulent channel flow. Let the mean flow U be unidirectional in the direction of X, and the wall at Y equal to H. Then, here UVW are the components of fluctuating velocity in the X, Y, and Z directions, and the Y is in the normal direction. And we have a simple relation written here for the Reynolds stress. And this represents the momentum transfer across Y. And if the so-called friction length number is high enough, there must be a range of Y such that Y is much less than H, half channel width. And then this must be negligible. And also, Y is much larger than friction length scale. Then this must be negligible. And in stationary turbulence, this must be negligible. And the existence of the similarity between homogeneous turbulence and wall-bounded turbulence has been known. This range is called inertial sublayer. And Tenex Lamley, for example, noted about the similarity between spatial structure of turbulent boundary layer and spectral structure in homogeneous isotropic turbulence. The similarity between the interscale energy transfer in HIT, homogeneous isotropic turbulence, and momentum transfer in wall-bounded turbulence can be seen by comparing the following relations. In HIT, Kallenhauer's equation is equivalent in the K space to the so-called Linz equation. And the integration with respect to K gives this relation for the energy transfer. And when the length number is high enough, there must be a range K such that the viscous term and forcing term and station term are negligible. This implies that under that condition, energy transfer is almost constant epsilon dissipation, independently of K. Similarly, in the inertial sublayer, integration of this mean flow equation with respect to Y give this relation. And under certain conditions, if the RE tau, friction length number is high enough, these three terms are negligible. This implies that the length stress is almost constant independently of HY nu, equal to U tau. Sorry, U tau is a so-called friction velocity, wall friction velocity. This similarity suggests that the role in the interscale transfer in homogeneous turbulence, the role played by epsilon and R or epsilon and K may be played by U tau and Y in the inertial sublayer. That is, if we may assume that inertial subrange can be characterized by epsilon and R as in K41, then we are attracted to assume that the inertial sublayer can be characterized by U tau and Y. And these terms are regarded to be as disturbances added to this equilibrium system. And the disturbance consists of two forces in stationary turbulence. One is large-scale forcing that is proportional to mean pressure gradient, and the dimensional analysis suggests that is proportional to Y over H. And the other effect is viscous effect that is in proportion to the viscosity, and the dimensional analysis suggests it is proportional to 1 over Y plus. Plus means non-dimensionalization by using unit wall unit. And if we apply the idea of LR linear response theory to B, that is Y derivative of Z, and Z is take Z UV or VV or WW, then we have some expression for this average. And this consists of two terms, and delta B represents the effect due to the disturbances. And here C, E, C, P, C, V are non-dimensional universal constants. Such relation has been known for B equal UV, and this implies that the normalized difference takes its minimum at certain Y value, and the minimum decreases with RE tau in proportion to RE tau to the power of -1/2. Such relation has been known, for example, in the textbook by Panton. And this conjecture by the LRT were tested by comparison with the N theta with turbulent channel flow with R lambda up to about 8,000. The symbol here shows the dn theta, and solid lines show the theoretical conjecture. The two coefficients were estimated by a fitting based on the data at the highest RE tau, that is about 8,000. It is seen that the conjecture where UV, VV, and WW agree well with DNS in an appropriate Y range, that is inertial sublayer. Now, the idea of LRT was applied recently to a single particle diffusion in turbulence. Let X be the Lagrangian, no, sorry, let A be the Lagrangian labeling. That is the position of a particle at the initial instant, say 0. And let V be the velocity at time t of that particle. And let delta V be the velocity difference between the time interval tau. If the length number is high enough, there must be a certain so-called inertial time subrange of tau that is much less than large t, the characteristic time scale of energy continuum eddies, and much larger than the column of time microscale. And the application of the idea of K41 to the second order moment of velocity difference gives this expression that implies normalized moment is independent of tau, time interval. This figure shows the DNS data by so forth and even, and the curves shift outwards with the increase of length number. By seeing this kind of figure, one may wonder, does the ratio in fact tend to a constant in the limit of R tends to infinity? Or maybe is K41 basically correct or wrong? In this problem, there are at least two kinds of disturbance that disturbs the equilibrium state. One is viscous effect or smaller scale effect, and proportional to nu. And if we assume this effect may be expressed in terms of something linear in nu, then the dimensional analysis suggests this is proportional to this term. And the other effect is due to the large scale effect. And it's natural to assume it to be in proportion to tau over t. Then we have some estimate for the second order moment. And this shows the comparison of the conjecture and the DNS data by Sofold and Jung. And here the symbol DNS data and the solid lines are the conjectures. And the non-dimensional coefficient was estimated by fitting based on the DNS data at each real number. And this expression implies that the magnitude of the difference takes its minimum as a function of tau at some value of tau, and the minimum decrease with R lambda in proportion to R lambda to the power of -2/3. And this exponent is in agreement with -1.65 at large R lambda reported by Barjona and Silva. They obtained this value by simulation using hyperviscosity. What time is it? Now let us move on to the effect of mean field. Let us consider first the effect of mean velocity gradient, Sij, and consider velocity statics, that is moment of velocity difference. Then, if the basic state may be assumed to be isotropic, then LRT suggests to introduce assumption 1, that in the limit of velocity gradient tend to 0, then the moments tend to some value independent of S. And if the basic state is isotropic, this must be isotropic. And if the disturbance is added as a mean share, then it gives response in this form that is linear in X. And that means for small but finite S, the response to the share is linear in S. And here C1 must be isotropic tensor because the basic state is isotropic. This relation is similar to the stress-strain relation for non-Newtonian fluid, but here this coefficient may depend on R. If in the inertial subrange, we may further assume that this equilibrium state is not only isotropic, but may be characterized by only epsilon and R, then we can have some scaling for the equilibrium state and the response to the disturbance in this form. And this idea can be applied to the second order moment as well as the third order moment. And in order to treat the incomplete condition, it is convenient to work in the wave vector space. And in the wave vector space, the collision spectra can be written as shown here. Here, delta Qij represents the response to the shear and can be written in this form. That means this can be characterized only by two scalar functions, A and B. And if we may further assume that the basic state can be characterized by K41, then A and B are shown to be represented only by two scalars. And this scaling is consistent with Lamrey's scaling. This implies that the Qijk can be characterized for Qij for any ij and direction of k can be characterized by only by two universal coefficients a and b. And this conjecture was confirmed to be consistent with DNS. And a study to derive this constant theoretically was made by using a closure approximation called Lagrangian renormalized approximation. And the analysis suggests that very large real number is necessary to reliably estimate the constant by DNS and or experiments. The idea of LRT was recently applied to statistics of velocity gradients. A naive estimate suggests that under assumption of the localness and in space and scale, the ratio of the magnitude of a mean shear effect and the coupling of small eddies of size L, the ratio is small, decrease with L under certain conditions, where S is the norm of the mean shear. According to K41, this ratio is expressed in terms of S and epsilon and L. And this ratio is shown to be much smaller for eddies of size L much less than so-called Coulson scale. Coulson argued that the scale must be much smaller than this scale. He argued in wave number space. And at eddies of size Kolmogorov scale, the ratio is expected to be linear in S and nu over epsilon square. And the LRT suggests to introduce the assumption that in the limit of gamma tend to 0, the moment of the velocity gradient, fraction velocity gradient, tend to constant independent of gamma. And this is function of only epsilon and nu. And for sufficient small but finite gamma, the response to the gamma is linear in gamma, and the coefficient C1 is function of only epsilon and nu. And the dimensional analysis gives expression for this quantity. And in long low layer in turbulent channel flow, it is known that the shear and energy dissipation rate scales with 1 over y. Here, epsilon dissipation, energy dissipation is expressed with bracket. This implies the ratio gamma is in proportion to y to the power of -1/2. And applying the LRT, we can derive second order expression of second order moments for any I and J component. And this slide shows the sum of the DNS data of turbulent channel flow with friction length number up to about 8,000. And it is seen that with the increase of Y, the moment approach to the isotopy value, it is 1 over 15th in this case for 1,1 component. And the difference between the isotopy value decrease with Y in proportion to Y to the power of -1/2, sorry, in appropriate range of Y, that is inner sublayer. It is also true for the other component. One can apply the idea of LRT, the estimate of the effect of mean shear on passive scalar statistics. And the application yields expression for mixed structure function. And if we assume that the basic state is isotopic, then this must be isotopic. And if we apply the shear to this basic state, then the response must be linear, and this coefficient must be function of only epsilon no, must be isotropic. And if we may further assume that in the inertial convection range, the basic state can be characterized by only chi, epsilon, and r, then we can derive some scaling. I hope I didn't miscalculate the dimension. And in the same way as for the velocity gradient, one can also derive estimate of the effect on the mean scalar gradients. What time is it?
You still have about 10 minutes, 10, 15 minutes.
15 minutes, okay. Let's skip the data. That is in the same way for the velocity gradients, we can estimate the influence of the mean shear on the scalar gradient. And for the case of Schmidt number much less than unity or order unity, then this scalar dissipation occurs at scale, so-called Obuch-Carson length scale. And the ratio gamma is estimated to be in S multiplied by K over epsilon square. And in the same way as for the velocity gradient, we can derive the moment of passive scalar gradient. And this must be function of chi, epsilon, and k. And the response to the shear is this form. And again, this coefficient is functions of only chi, epsilon, and k. And dimensional constellation gives some expressions. And in long-law layer, gamma, sorry, this is piece order. The P is the order of this moment. And in the long-law layer, gamma is in proportion to y to the power of -1/2. Now let us consider the effects of mean scalar gradient. Mean scalar gradient. And many studies of the statistics of scalar field under uniform mean gradient have been made. That is, G represents the gradient of mean scalar gradient. And the LRT suggests that if the basic state is isotropic, then the system responds to the mean scalar gradient in proportion to G. And here CE and C1 must be isotropic tensor depending on R. And this idea yields conjecture on the scalar correlation and mixed correlation. And in the wave vector space, the correlation, the conjecture gives this expression that is anisotropic. And this figure shows a comparison of the conjecture and the DNS data related to this anisotropic part. And this DNS data were produced by and analyzed by Yoshimatsu-san. And the smooth curve show the theoretical conjecture, and the zigzag curve by DNS data. And it is seen that the conjecture on the direction dependence are in good agreement with DNS data at high K mode. Many curves show the difference of the wave number range. If we may assume not only the isolate, but also some K41 idea, that is, if in the inertial convex range, the basic state can be characterized by chi, epsilon, r, then we have some scaling. We can include, identify particular scaling by dimensional analysis. And this idea can be applied to the term representing the contribution F due to the mean scalar gradient on the mixed structure function presented in this, that is Yagonov's relation. And this third order structure function is not in general isotropic because of this non-isotropic scalar input. And the problem is how to estimate this inference. And this is given by the second order moment, mixed second order moment. And applying the LRT, we can derive this expression. And this scaling is in accordance with Ramirez scaling. And this angle dependence is similar, but a little different from that proposed by Goto, Watanabe, and Suzuki. They suggest that the coefficient, here P is the Legendre polynomial. They suggest that they argue that the coefficients are determined by Lagrangian correlations. After analyzing the DNS data, Yun, Fuku, and Sunima-san noted that the structure function is systematically large. The function is normalized in appropriate sense, and the structure function is systematically large when R is taken parallel to the mean gradient direction. And since the structure function in experiments are usually measured in only one direction, this result suggests a need for caution in reference on Yagonov's relation. This means that one need to be careful about the direction dependence, and this estimate may tell something about the direction dependence. And here we considered only the influence of mean scalar gradient. The similar idea can be applicable to the influence of dissipation gradient and of epsilon and chi. In the same way for the mean shear, one can also derive estimate the effect of mean scalar gradient on the dissipation in the statistics. And under appropriate and suitable assumptions, we can show that the influence this term is smaller than this term. And assuming in the inertial convex range, the basic state can be characterized by chi, epsilon, and L, then we can show this ratio is small under certain conditions. And in the case of Schmidt number much less than unity or order unity, we have this expression and can derive at the moment that in the limit of gamma tends to 0, this is function of only gamma, chi, epsilon, and kappa. And for sufficiently somewhat finite gamma, the response due to this gradient is in proportion to gamma, and this coefficient must be function of only kappa, epsilon, and chi. And by dimensional consideration, we can derive these expressions. What time is it? Okay, let me summarize. First, the influence of small but finite disturbances such as viscosity, diffusivity, mean velocity gradient, and mean scalar gradient in general decrease with the decrease of the disturbances, but with different rate or different phenomena or observable. Some estimate for the approach rates can be made from the viewpoint of LRT. LRT gives not only the approach, but for some cases, the direction dependence also. And the difference from the idealized or simple scaling law are not necessarily intermittency corrections. Some conjectures based on LRT agree well with DNS experiments, but some remain to be tested, in particular, some conjecture on scalar field. Here I ignored intermittency effect, but it may be of interest to incorporate intermittency models for epsilon and chi. And last at least, not least, is it's fun to find similarity among apparently so different phenomena. Finally, this and the next page show references of figures and quotation used in this talk. This is the end. Thank you for your attention.
Thank you, Professor Kaneda. You told us a lot, but there was clearly a consistent message there about all these different fields. We have a question from Professor Pandit.
Hello, Yukio. Thank you for your comprehensive and thought-provoking talk.
Thank you.
I just had a question. You keep on referring to the state as an equilibrium state, and therefore you use linear response theory.
Yeah.
However, strictly speaking, it is a non-equilibrium statistically steady state.
Yes, yes.
And therefore you expect a generalization, and there's a paper that you must know well, last year, JFM, Matsumoto, Otsuki, Oshida, and Goto, who suggests that we should go beyond straightforward linear response theory to Harada, Sasa, and things like that.
Yeah.
Do you have any comment on that?
Sorry, I'm sorry, I haven't read it.
Okay, it's just that, I mean, naively, you would expect that fluctuation dissipation relation would not hold for a non-equilibrium system. Now, it is possible that for the quantities that you consider, the differences between the two are very small. So, I mean, you know, it comes as a surprise that straightforward linear response theory should go through. That's all I'm saying.
Yeah, yeah. The point is that unfortunately we don't know, we don't have a Hamiltonian, or we don't know about the equilibrium state. Even about the existence we don't know. But so my use of the terminology equilibrium may be misleading. The only assumption made here is that there must be something characterized by something, and unfortunately we don't know by what the system can be characterized. But for example, at least it may be safe or interesting to assume that there are some basic or asymptotic state that is statistically isotropic. And if we may assume isotropy of the basic state, only the assumption of isotropy tells something. That is, repeat, we don't know exactly what is the equilibrium, or what is a basic state, or what is the asymptotic state. And then we assume something and see the response. That is, we can observe response in experimental DNS. Then, knowing response may tell inversely something about the basic state. That is, in statistical mechanics of equilibrium system, we know in advance what is the equilibrium state. In turbulence case, we don't know exactly the equilibrium state, or even the existence we don't know. But if we assume something and we observe response, then response may tell us something about the asymptotic state. That is my strategy.
Thank you. Any other questions? Well, thank you, Professor Kaneda. We're going to go we're going to go have coffee here, but I suppose it's too late for you for coffee. Thank you. Have a good evening.
Thank you.